Welcome to the video lesson on Newton's second law in friction. Newton's second law is a huge topic in physics, and in this rest of this course we'll see this referred to all throughout the rest of the year, as is friction, and another big topic in this unit. Let's start by talking about friction. We're going to have this conversation over here. The formula for friction that you'll find on your reference table says FF equals mu. That's a lowercase Greek letter. You may also recognize this as the symbol for micro, the metric prefix micro, and then Fn. Let's cover what these three variables are, and then we'll talk about the relationship and how they're used to calculate friction. Friction, of course, is a force. It's a force that always opposes motion or intended motion. And so we use the symbol F, subscript F, for force of friction. But in reality, we'll always be dealing with two types of friction. There'll either be static friction, the friction that acts on an object when it's at rest, or kinetic friction, the friction that acts on a body when it's moving. And because of that, this F will be replaced by either an S or a K, depending on the situation. The other thing to note here is, and this is pretty common knowledge among most people, is that static friction is always greater than kinetic friction. That is to mean that it takes more force to get an object broke free from its static state than it does to keep it moving, moving across the surface. So it takes more force to break it free of static friction than it does to keep it moving. So we say that static friction is always greater than kinetic friction. The symbol mu in this equation stands for the coefficient of friction. One of the most common mistakes made by beginning physics students is confusing the difference between force and coefficient of friction. Force is the amount of effort to overcome it, and the coefficient is actually a relationship, a ratio, or a number. We use a decimal. A number that reflects the relationship between the two materials that are in contact with each other. And so that coefficient of friction, again, will either be a static coefficient or a kinetic coefficient. And just like the force, the static coefficient will always be greater than the kinetic coefficient. The last variable here we have here is F subscript n, which you already know as normal force. Note that this is all that friction depends on, is the coefficient, which depends on the two surfaces in contact with each other, and the normal force. All right, now we're going to take this concept and apply it to Newton's second law. Newton's second law, as appears on your reference table, says F net equals ma. I like to teach a mathematical approach to Newton's second law, which is sigma F equals ma. You may recognize the symbol sigma, the uppercase Greek letter, as the same symbol for summation. So another way to say this is that the summation of forces is equal to ma. And I'll explain this more as we go ahead. This is the approach that you're going to see taken in class, is that I'm going to use sigma F. So the summation of forces that act on an object create a net force, which causes that mass to accelerate, or in some cases to not accelerate, and more to come on that here in a moment. What's really important in doing Newton's second law problems is you start out with what's called a free body diagram. And a free body diagram shows all the forces acting on an object, and only the forces acting on an object. To model this for you, I'm going to use number 11 from the problem set. So if you need to get that out and have that handy to look at, go ahead and do that. I'm going to pause this video and go over to that problem so we can talk about it, and then come back and talk about its solution as a model of how to use Newton's second law. Here we are at the problem number 11 out of the problem set, which says if you use a horizontal force of 30 newtons to slide a 12 kilogram wooden crate across a floor at constant velocity, what is the coefficient of kinetic friction between the crate and the floor? As we have modeled in other problems, we go through and we label known information and the variable associated with that. So we have a horizontal force of 30 newtons, so we'd underline that and label it F. We have a 12 kilogram wooden crate. By the units of kilograms, we recognize that as the mass of the wooden crate. We note that it's moving at constant velocity. That's very significant, so I've underlined that. And they want to know what is the coefficient of friction between the crate and the floor. And so since it's moving, and they say coefficient of kinetic friction, I've underlined that and labeled it mu k. Now back at our notes here, from the problem that we just described, we draw a free body diagram. We have the forward force of 30 newtons. We'll point that to the right. We have the friction, kinetic friction, acting backwards on the object, pointed to the left. We have the normal force of the surface pushing back up on the object, pointed up. And of course we have its weight down towards the center of the earth, down, and we've labeled that mg. We also, I like to include a motion arrow that reminds me what direction this object is traveling, and the significance of that in doing Newton's second law problems, and this is very important, is that the direction of motion tells you which forces in your problem end up being positive. The direction of motion indicates the forces that are positive. So because this object is going to the right at constant velocity, more on that to come, that means this force would end up being positive, and friction being in the opposite direction would be negative. Okay? You'll hear that emphasized throughout the entire time here. Little side note here, we have a little Newton's second law calculation going on over here in green. And you notice that what's happened is that the forces have been summated that are perpendicular to the line of motion. Okay? Well, typically we call up positive, so we have Fn minus mg. And you'll note that this object is not accelerating vertically, so the a value is 0, making the product of m and a also 0. So the summation of forces would be Fn minus mg equals 0. Well, clearly if we add mg over to the other side, the normal force is equal to the weight. Because the object is not accelerating vertically, and there's only two forces, and they're opposite each other, these two forces have to be equal to each other. This is huge. For an object on a horizontal surface in this course, almost all the time, the normal force will be equal in magnitude to the weight of the object. All right, moving on. Now to solve our problem here. The first thing after you draw your free body diagram, the first thing you do is write Newton's second law expression, sigma F equals ma. The next question you ask yourself is this object accelerating? We are reminded by reading the problem previously that it's moving at constant velocity. So the answer is no. Since a is 0, the product of m and a is 0, so we write equals 0. Our next step is to summate the forces. What that means is we consider all forces that lie in the same plane as the motion. Since F is pointed in the direction of motion, it is positive. And since Fk is in the opposite direction of that, it is negative. So F minus Fk equals 0. What this clearly indicates to us, if we add Fk over to the other side, that these two forces are equal. Since we know the force is 30 newtons, provided in the problem, is equal to Fk, from our previous lesson on friction, we also understand that the kinetic friction is calculated by mu k times normal force. And from the lesson up here in green, we know that the normal force is equal to the weight. So we make all the connections here to say that the 30 Newton forward force is equal to the friction force, equal to mu k Fn, and Fn is equal to mg. So the equation turns out to be mu k mg. We now substitute values that we know. We're looking for the coefficient of the kinetic coefficient here, and we know that the mass is 12 kilograms and that g is 9.81 meters per second squared. Solving from UK, then we get 0.255. Our answer should be to 3 digits. And note, there are no units of coefficient of friction. It is one of the 2 quantities in the entire course that you get away with without putting units because there aren't any. That, of course, comes from the fact that if you solve for the coefficient, it'd be the friction force divided by the normal force, which would be newtons divided by newtons, and newtons cancels. So there you have it. There's your lesson on friction and a brief lesson on how to use Newton's second law. And you will hear this process described in this video done over and over and over again as we continue to do problems from the problem set.